So in module one, we talked about kind of the historical trends in computing from an engineering perspective. In module two, we're going to talk about the more modern trends. So really the thing that you need to be aware of as engineers kind of starting your training in 2023 is what I will call the big data revolution. And I hate that word, but here's an interesting thing. I want you to start by focusing on this screenshot that I took from Facebook and just ignore the date for now. It's an IBM post that says 90% of the data in the world has been created in the last 2 years. And if you hear about that, you probably think that this is something that's relatively new because we're all aware of all of the data that we generate every day, mainly because we just have all of our phones around us. And our phones can take videos, they can take images, and generally speaking, to represent a video or an image takes a lot more information than to represent text or even audio for that matter, particularly since most video, of course, has audio with it. However, note that this quote actually came from 2012. And really what was going on in 2012 is there was kind of this rise in tendency of enterprises or companies to try to capture as much data as they could in order to monetize, particularly around that time frame. In addition, you have kind of the rise of social media, the rise of search, and the capability to really just capture a lot of information that previously wasn't recorded. So I would argue that if it was 90% of the world's data generated in the last 2 years in 2012, who even knows what it is in 2023? And here's the reason. There's a lot of different trends in computing that are causing us to generate more data and capture it. One that you want to be familiar with is an acronym known as IoT, or the Internet of Things. Another thing that's really driving this kind of data capture revolution, or the second data revolution, is 5G, or fifth generation standard for actual broadcast wireless communication for cell phones. And we'll talk about how all of these go together a little bit in the latter slides, but for now, just take them all as enabling technologies that engineers have created in order to kind of capture more data of the world around us. In addition, you not only have to be able to capture the data via IoT and sensors and transmit it to wherever you're going to store it, you need really flexibility in storage, which is this ideal of cloud computing. And I'm not sure if you're all familiar with cloud computing, but the main thing that you want to know is it's really not a new idea. It's the same actual hardware that companies used to actually have integrated on premise. However, now, since it's actually off-site and available to kind of rent as a service, it provides much more flexibility to kind of scale your needs in real time to whatever, in this case, amount of storage you need. But you don't just have to use it for storage. You can use it for compute or web hosting as well. In addition to those three trends, there's kind of this idea that there's really a push for individuals to share their data on these open source type of repositories. And we'll look at that a little bit in a minute. So what I want to say about data for non-data engineers, of course, you can be a data engineer. I didn't notice on the initial discussion board that any of you said you wanted to go into data. A lot of you mentioned that you were interested in AI as an enabling technology. And of course, data is kind of the driving input for artificial intelligence models. However, you should know that really there's this expectation amongst like kind of all educated people now that you have a fundamental amount of data literacy, that you know how to work with data, you know how to interpret data, you know how to visualize it, clean it, and so on. So that expectation is going to be even higher for engineers because people are going to expect that you're the numbers person, you're the quantitative person. So these are just things that you should be able to do. So generally speaking, if I had to define what it means for an engineer to be data literate, I would say that it's expected that you have the capability to interface with common data sources. So those can be actual the generation of data, like actually cooking up into hardware and being able to capture information that's recorded from that hardware, or actually just taking data that someone else has already captured that's in a computer file and being able to work with it. In addition to just having a bunch of data, which under the hood is all stored as ones and zeros, as we spoke of in the last lecture, you want to have the capability to extract value out of it. If it's just a bunch of numbers, that's not providing much value. In addition, you want to be able to communicate that to others. So there's lots of different techniques that you can talk about. A lot come from statistics. If I have a bunch of numbers, I can talk about kind of an average value, or I can talk about a spread of a value through some measure of dispersion. So engineers are all expected to have those basic statistical summary capabilities. In addition, we want to be able to take that information and kind of communicate it in a form that our brains are most wired to handle. And if you know anything about the way that your brain is made up, the majority of the gray matter is actually devoted to being able to process visual information. That's one of the key kind of differentiators of the human brain relative to other brains. So pictures are worth 1,000 words. If you can take data and summarize it in visualizations, it's going to get across a lot better to the stakeholders. And more recently, kind of maybe the most important thing about that people will expect that engineers can do with data, they will expect that they can actually take that data and train models that can make predictions about future scenarios or future data. And that, of course, is the ideal of artificial intelligence. So even in order to do this, what kind of skill are you going to need to be able to do? Of course, you could do a little bit of summary statistics or visualizations just using a spreadsheet that wouldn't require actually any coding. However, it is going to be much, much easier if you do these tasks using some type of code or some type of software development. And we'll start to look at that in next week of the course. But do note that as time progresses, the amount of low code or no code solutions that allow you to do those sorts of things is increasing. So going back to those different technology trends that I mentioned in the first slide of this module, we talked about IoT, or the Internet of Things. What is the big idea behind the Internet of Things? Well, if you look around you, a lot of stuff that used to not be smart in your home may actually have some smart capabilities now. You had these low-tech objects that now have been kind of improved in order to capture information from the world around them. And the actual devices that allow them to capture that information are just generally called sensors. In addition to being able to capture that information, these devices now oftentimes will have some form of computing actually integrated within them. They have some kind of basic processing to not only get numbers that describe the environment, but actually do some mathematics on those. In addition, it's not going to be very useful if you're just continuously capturing information, maybe doing some math on it, if you don't have the capability to send it anywhere. Because if you have to store everything locally, even though, as we mentioned in the last video with Moore's Law, memory density is increasing, you're eventually going to run out of space. So that is kind of the key attributes of an Internet of Things type device, in my opinion, those three capabilities: the capability to sense, the capability to process, and the capability to communicate. It might not be on the actual standard internet. It might just be to another local storage device kind of in your network. So what are the drivers that are making IoT more feasible? Well, that Moore's Law phenomenon that we talked about in the first module. We can make underlying transistors more dense, which allows us to have smaller form factor computing capacity as time moves on. In addition to having smaller and cheaper computing, we need to have the capability to have commodity level, and what that means is basically just cheap and available in large scale sensors, things like temperature sensors or pressure sensors or humidity sensors. If we want to know what's going on in the world around us, we have to be able to quantify it, and sensors allow us to do that. In addition, as we talked about on that first slide, how do we have the capability to handle all this information offloading from these IoT devices? Well, we need better communications, and better typically means higher bandwidth, or the ability to send more information from across a channel. And that is really enabled by 5G technology, as we talked about on the first slide of this module. So just note that there are some other words for like IoT type phenomenon. You might have heard a term like edge computing. Edge computing generally refers to IoTs where the processing capability is more sophisticated. Maybe you have the capability to process images. You have a graphical GPU embedded in some kind of like NVIDIA Jetson platform, if you've heard of that. But the main thing you want to know from the slide is what IoT stands for: Internet of Things, the basic attributes that it has: sensing capability, processing, and networking, and that it's really helping to drive the data revolution in modern times. So what is artificial intelligence? I said that was another driver of the modern data revolution. Well, the key thing that I want you to see in these two first definitions is that we really still don't agree on what AI means as an umbrella term. Is it really just kind of creating computers that have the capability to learn and generalize like humans? Can they perform some tasks that are just really hard to code hard rules for, like how to do visual perception or how to recognize speech? If you think about it, for really, really easy cases, it's easy to tell a computer to tell the difference between a 0 and a 7. But if I start to angle my 7s a little bit or write them a little sloppily, and if I throw another digit that looks like a 7 in it, you're going to have a hard time describing the set of rules that a computer needs to follow to do this thing that a 5-year-old can do really easy. They can tell what that number is, even if it's a little bit turned or it's a little bit messy. So that's the idea behind AI. Don't give it rules to tell it how to do it. Give it a bunch of data and allow it to learn the underlying patterns. So those definitions of artificial intelligence are continuously changing. One thing I do want you to know is that machine learning, which is a word that you hear a lot, which is a subset of artificial intelligence. So all ML is AI, but all AI is not ML. Really is about doing that task that I just mentioned, where you take a data set and you try to allow a computer to learn a model from that data without being given explicit instructions, without being really programmed. So classical machine learning, what you usually do is take your raw input data and extract some features that are assumed to be kind of related to whatever label you're trying to learn. In modern machine learning, which is known as deep learning, you try to learn those mappings directly. So the easiest example here is, to give you an example, if you're trying to learn like a computer vision classifier to tell in an image whether it's a cat or dog, modern deep learning just takes the image directly and spits out a 1 or 0, whether it's a cat or dog. Traditional machine learning would try to attract features of that image and then do that manually, and then learn a mapping between the features to the actual labels. So if you're interested in digging into that more, feel free. I know it's really weird to go over that in the second week of class, but I've found in the 2 semesters since I've redesigned this course to really go over some emerging tech that people really like this stuff and they're able to pick it up. So on the data repository side of things, if we're going to generate all this data, there's got to be some kind of use case for it. And really one thing that's going on in engineering is this transition to the open source movement. And computer scientists have been ahead of us for a long time. They've always liked to share their code. And we're kind of moving that way, even with actual things. So if you click on that link and look at Thingiverse, you'll see that there's actually an open source movement in hardware. If I actually kind of design some widget and have a 3D model that I 3D print, I can share it with others. And as I mentioned, GitHub is really the driver for sharing information from a coding perspective. So one thing that you want to note is that there is a lot of push to just share your data now, since that data can be used for all those different functions that we talked about in a prior slide. So if you're interested in some data sets that are freely available online, check out the Kaggle data sets. There's also Kaggle competitions that are interesting. Big ML, really there's lots of different data repositories that are available. Some other things that I think are important to be aware of and dig into, they're going to be particularly relevant by the time you graduate, is this idea of quantum computing, which, as I mentioned in the previous module, could totally revolutionize the way that our computers look in the future. The idea of cloud computing, meaning that when you need a new computing investment, you don't actually buy hardware, but you rent the service, whether it's storage or compute, which is enabled by a connection to the internet. And then edge computing, which is rather than taking all this information in an IoT, capturing it and sending it up, maybe we're storing way too much information, and a better way to do it is to do some processing on the edge and only send up kind of summary or relevant